Good morning students. Today we will see a derivation on collision. So what is collision? A collision is said to take place, that means when two bodies when physically collide against each other, right? When they just come into contact with each other with some velocity, right? Then that is called a collision, right? So there are two types of collision: elastic collision and inelastic collision. In elastic collision, in elastic collision, a collision is said to be elastic when the two bodies, which I am showing over here, the red and green, with the initial velocity u1 and u2 and respective masses m1 and m2 and respective velocity, final velocity as v1 and v2, when they collide, right? Then on this collision, which is elastic, the two things are conserved, right? The two physical quantity is conserved. What is that? One is momentum, another is kinetic energy, right? But the only difference between the elastic and inelastic collision is that in elastic collision, the conservation of kinetic energy is not happening in inelastic, right? So here we will just see the elastic collision, right? So in elastic collision, when the two masses, which I have shown over here, then for the two masses just on collision, the momentum and kinetic energy is conserved. That is before the collision, and after the collision the momentum of the system will be same and kinetic energy of the bodies will be same, right? So we can say very easily that the two bodies m1 and m2 will be having the conservation of, will follow the conservation of momentum and the kinetic energy during the elastic collision, right? So I am writing over here that momentum and kinetic energy is same. That is before the collision, the momentum of the mass m1 and m2, when you will add up, then after the collision the momentum of the mass m1 and m2 will be same. Similarly it happens for the kinetic energy before and after collision, right? So now just I am highlighting over here before and after collision, momentum and kinetic energy is conserved, right? Now let us see how we are deriving this, right? If we are considering the momentum, then a momentum, we know that momentum before the collision, right? You know, momentum is mass into velocity, right? So we can see that momentum before collision is equal to the momentum after collision, right? What momentum of what? Momentum of the two bodies m1 and m2, as we have considered for both the masses having the mass m1, initial velocity u1. So initial momentum of before the collision for mass m1 will be m1 u1, and initial momentum for the mass m2 will be m2 u2, that is before the collision. Similar, the momentum after collision will be m1 v1 plus m2 v2, right? Now just bringing the terms with m1 into the LHS, we left with m1 times u1 minus v1 equal to m2 times v2 minus u2, right? Now considering the second part of the criteria of elastic collision, that is the kinetic energy, which is also conserved, right? So before the collision and after the collision, the kinetic energy of the bodies m1 and m2 before the collision will be equal to the kinetic energy of the both the bodies after the collision, right? Now we can write before the collision what will be the kinetic energy. Kinetic energy is equal to half mv square, right? So here before the collision the velocity will be u1 for mass m1 and u2 for mass m2. So the respective kinetic energy for the both the bodies will be half m1 u1 square plus half m2 u2 square, and after the collision u1 will be converted to v1 and u2 will be converted to v2. So after the collision the kinetic energy will be equal to half m v1 square plus half m1 v1 square plus half m2 v2 square, and half will be cancelled out into the LHS and RHS because all the four terms are having 1/2 in their coefficient, right? So we are left with m1 square plus m2 square equal to m1 square plus m2 square, right? Now, as we did earlier, bring the terms with m1 into the LHS as a like term, and similarly the terms with m2 into the RHS, right? So segregating the like terms together, we are having in the LHS m1 square minus v1 square inside the bracket, and into the RHS m2 times v2 square minus u2 square, right? We know that u1 square minus v1 square is just resembling with a formula of a square minus b square, right? We know that a square minus b square is equal to a plus b into a minus b. Just break u1 square minus v1 square based upon the same formula. So into the LHS we are left with as shown, and similarly into the RHS break v2 square minus u2 square on the formula of a square minus b square, that is m2 times v2 minus u2 into v2 plus u2, right? So what we have used over here, that is a square minus b square. You use the formula and just splitted the terms as a plus b into a minus b, right? Now here you can see the initial derivation as shown in red color. Just mark it as equation number 1, and here as we derived as equation number 2 in green. Now dividing the equation number 2 by equation number 1, what we will have in the LHS, the terms m1 into u1 plus v1 u1 minus v1 divided by m1 times u1 minus v1. Hope you are able to understand. u1 minus v1 will be cancelled out over here into the LHS. Similarly into the RHS, the term will be divided by m2 into v2 minus u2, and v2 minus u2 will be cancelled out into the numerator and denominator of RHS, right? Here I am cancelling the same terms into the LHS and RHS. So what we are left with? We are left with the term m1 into u1 plus v1. But you can see m1 is also common into the LHS and RHS. So we can cancel the m1 here and m2 into the RHS, right? So in the LHS we are left with u1 plus v1. u1 plus v1 is equal to u2 plus v2, because v2 plus u2 is equal to u2 plus v2, right? And now bringing initial velocity to the LHS, we are left with u1 minus u2 into the LHS, and into the RHS the final velocities will come, that is v2 minus v1. So this is a relation we derive over here, that is u1 minus u2 is equal to v2 minus v1, right students? Perfectly fine. Now what we will do, let us see on the next page, right? This is the equation number 3 just mentioned, I am mentioning over here. In the next page we see by equation number 3 which we have derived, u1 minus u2 equal to v2 minus v1, right? Here v2 can be written as, since v2 can be written as into the RHS as, just do one thing, leave v2 into the RHS and bring other terms into the LHS. We can see u1 minus u2 plus v1 is equal to v2, right? Why we did it, we will just show you here, right? So v2 can be written as u1 minus u2 plus v1 from the equation as derived by equation number 3, right? And by equation number 1 we know that m1, the conservation of momentum, that is m1 times u1 minus v1 equal to m2 times v2 minus u2, as shown into the black color by a black pen, right? So here just replace this value of v2 into the RHS. So into the RHS we are having m2 times u1 minus u2 plus v1 minus u2, right? So what you will get into the LHS, m1 u1 minus m1 v1 is equal to into the RHS m2 times u1 minus m2 times u2 plus m2 times v1 minus m2 times u2. So here you can see m2 times u2 is 2 times, so I have added it over here. So written the second term into the RHS minus 2 times m2 u2, right? Now do one thing, just bring the like terms with v1 into the LHS, right? So what we will see, minus m1, so bring v1 as common or minus v1 as common, so m1 plus m2, because m2 v1 when coming into the LHS will become minus m2 v1, right? And since v1 is common, minus v1 is common, we are left with m1 plus m2 into the LHS, right? And into the RHS you see m2 times u1, the first term of the RHS, m2 times u1 minus 2 times m2 u2, right? And bringing the leftover term into the LHS, that is m1 u1 to the RHS, it will become minus m1 times u1, right? So just solve this, just solve to get the value of v1. Here you can see minus will cancel out, so the sign of m2 u1 is plus, so 1 minus will be there. After deducting 1 minus from the plus sign, 1 minus will be left, and other 2 minus terms into the RHS will be cancelled out. So into the LHS we have v1 times m1 plus m2 is equal to m2 times u1, and into the RHS we can write the terms as shown over here, right? Now we can see that into the next step the v1 can be segregated, the value of v1 can be identified. I did some mistake over here. Yeah, we can see, because minus m2 u1 was there into the RHS, so this will be the coefficient of the sign of minus m2 will be minus, so I am just correcting it over here with black pen, right? So right, so m1 minus m2 times u1 divided by m1 plus m2, which is coming from the LHS, right? This is the first term of RHS, right? Plus 2 times m2 u2, 2 times m2 u2 divided by m1 plus m2, right? So the final velocity of the body after the collision, the final velocity of the first body, let us say when the two masses which were colliding, the final velocity of the body after the collision can be derived by using this formula, that is m1 minus m2 by m1 plus m2 into u1 plus 2 times m2 by m1 plus m2 into u2, right? Similarly, putting up the value, we can very easily find out the value of the final velocity of the second body, that is v2, right? By using the equation 1, 2 and 3 as we have already derived earlier, right? So the v2 will be like this, the formula will be like this. You can see it's very easy to remember. You can see the formula, it's very easy to remember. The numbers are changing, the masses, in place of m1 write and m2, in place of m2 write m1, right? And in place of u1 write u2, and in place of u2 write u1, right? So the final velocity of the body after collision, the second body will be v2, which will be equal to m2 minus m1 by m2 plus m1 into u2 plus 2 times m1 by m1 plus m2 into u1. So in this way we have derived the formula for v1 and v2 for two bodies which are undergoing an elastic collision, and in elastic collision the conservation of momentum and kinetic energy is happening, right? And the difference between elastic and inelastic is that the kinetic energy is not conserving in inelastic